So now, in a nutshell, one of the special things about semiconductors is that current inside semiconductors is composed of two components. There is a current due to electrons and there is a current due to the movement of holes, known as the hole current. Now, while the physical or the actual movement of electrons and holes is in opposite directions, the resultant current is in one direction, or the resultant current is added. Now, why is this so? Because if you have similar charges or same kinds of forces which are acting in opposite directions, or same charges which are moving in opposite directions, the net effect will be subtraction of the two. But if you have opposite charges which are moving in opposite directions, their net effect is added. So even though the physical movement of holes and electrons is in opposite directions, the resultant current or net current is actually added. The second important thing to understand is that the free electrons are actually in the conduction band, whereas the movement of holes is inside the valence band. And the movement of holes is actually in effect a movement of those electrons which do not have enough energy to move to the conduction band, but they only move from one place to another inside the valence band. So we can say that the hole current is basically due to bound valence electrons that are not as free as conduction band electrons. Therefore, they only move from one covalent bond to another, and their movement from one covalent bond to another is basically the movement of holes. This then naturally brings us to the mobility of holes and electrons. Now, conduction band electrons are more free, and therefore they have a higher mobility and they constitute a current that is more smooth. Whereas holes, they're not as free as the electrons inside the conduction band. In fact, we know that the movement of holes is actually a movement of valence band electrons, which are only able to jump from one covalent bond to another. Therefore, the mobility of holes is much lesser than the mobility of electrons. Now over here, the mobility of electrons in silicon is listed, and it is 1350 centimeters square per volt seconds, whereas the mobility of holes, which is less than half of the mobility of electrons, is 480 centimeters square per volts second. We now move to the second type of semiconductors, or I would say the more useful kind of semiconductors, which are extrinsic semiconductors. Now, the problem with intrinsic semiconductors is that their behavior is unpredictable, and that is because their conductivity or their working is heavily dependent on temperature. So now if you have a semiconductor device made from an intrinsic material, it will not conduct or not work at all, let's say on the K2 mountain or in the hilly sides of Pakistan, because obviously the temperature there would be low, and at very low temperatures the conductivity of semiconductors is zero. And of course it will its behavior, its working will be completely different if you carry the same device to inner Sindh, to the cities of Sibbi or Jacobabad during summer months when temperatures are extremely high. So you can't have an electronic device whose behavior is heavily dependent on temperature. Therefore, in order to circumvent this problem, or in order to overcome this problem, we dope the intrinsic or pure semiconductor materials with certain kind of controlled impurities, and what we get is extrinsic semiconductors. So what are extrinsic semiconductors? Extrinsic semiconductors are basically doped semiconductors. And what is doping? Doping is the process of adding certain controlled amount of impurities. So extrinsic semiconductors are basically impure semiconductors to which certain controlled amount of impurities have been added in order to modify their behavior and working, and in order to make it more suitable to our needs. Now, there are two kinds of dopings or two kinds of impurities which are added. There is donor doping and there is acceptor doping. Now, what is donor doping? Donor doping or donor impurity is the one which gives or which results in an abundance of electrons. And the result that we have is N type of semiconductors. Acceptor impurities are those which leads to an abundance of holes. And what we get is P-type semiconductors. We are now going to look at the atomic structure of N-type semiconductors and P-type semiconductors in more detail. In order to form N-type semiconductors, we add a donor impurity. A donor impurity is an element from group 5 of the periodic table, such as antimony, phosphorus, or arsenic. Now, as you can see in this figure over here, that when phosphorus or any other group 5 element is added in a controlled or a small amount to pure or intrinsic silicon, a phosphorus atom replaces silicon atom in the crystal structure. Now, phosphorus or any other group 5 element has 5 valence electron as compared to, of course, silicon or semiconductor materials which have 4 valence electrons. So once we add an element of group 5 as an impurity to pure or intrinsic silicon, and it replaces a silicon atom inside the crystal lattice, what we have is that there is an extra electron present in the structure, because 4 of phosphorus's valence electrons form covalent bonds with neighboring 4 silicon atoms. However, the 5th valence electron is now free. It is now extra. Therefore, in N-type materials, when we add donor impurities, now the name donor, which is also very intuitive, must also make sense that it is a donor impurity because it donates electrons. So when to pure or intrinsic semiconductor, we add a controlled amount of a donor impurity, which is a group 5 element, we have an excess or an abundance of free electrons. And this gives us N-type semiconductors. So N-type semiconductors are those which have an abundance of electrons. Now, P-type semiconductors, in contrast to N-type semiconductors, have an abundance of holes. In order to form P-type semiconductors, we add acceptor impurities to pure or intrinsic silicon. Acceptor impurity is an element from group 3 of the periodic table. It could be boron, gallium, or aluminium. Now, boron, or for that matter, any other group 3 element, when it is added to pure or intrinsic silicon, a boron atom replaces a silicon atom inside the crystal lattice. And now, because boron, which is a group 3 element, has 3 valence electrons, it is able to form 3 covalent bonds with the surrounding silicon atoms. However, in the 4th covalent bond, the 4th covalent bond is incomplete because boron does not have the 4th valence electron, which it can contribute to that 4th covalent bond. Therefore, because boron doesn't have the 4th valence electron, it in effect creates a hole or a vacancy for an electron. This way, by the addition of an impurity of an element from group 3, we are able to create an excess or an abundance of holes inside the semiconductor. And this gives us our P-type semiconductors, which have an abundance of holes. So now in N-type semiconductors, Nn is the density of electrons. This Nn, the density of electrons, is basically a sum of 2 components. One is the density of electrons donated by donor atoms, and the second is the electrons which are generated through ionization, because you know that the process of ionization and recombination are nevertheless always taking place. So in an n-type semiconductor, the density of electrons now is a sum of two components. Density of electrons, which is donated by the donor atoms, as well as its own internal electrons, which are thermally generated. So now because the density of electrons which is donated by donor atoms is much larger than the electrons which are thermally generated through the process of ionization, we can say that the density of electrons in an n-type material is approximately equal to or is the same as the density of electrons donated by the donor atoms. Similarly, in p-type semiconductors, Pp, which is the density of holes, is a sum of two components. Holes which are added by acceptor atoms and the thermally generated holes. Same as n-type materials. Now because the density of holes which is added by acceptor atoms or which is added by impurity is much greater than the holes which are generated as a result of ionization, we can say that the density of holes in a p-type material is approximately equal to or is almost the same as the density of holes which is added by acceptor atoms. Now we already know from our knowledge of intrinsic semiconductors that the product of N and P, which is the electron density in an intrinsic semiconductor and the hole density in an intrinsic semiconductor, is equal to N intrinsic square. Ni square or N intrinsic square is the density of electrons inside an intrinsic semiconductor squared. Now over here in an extrinsic or an n-type semiconductor, the density of electrons N is now Nn, which is approximated by capital Nd, which is the density of electrons donated by the donor impurity. And however, the density of holes P is the same as, let's say, in an intrinsic semiconductor, because holes have not been added by any impurity. Holes are the ones which are still being generated as a process of ionization. So the holes, the density of holes in an n-type semiconductor, P of n, which is density of holes in an n-type semiconductor, is equal to Ni square divided by Nd. Now, this is the important thing in an n-type semiconductor is, now we know basically that in any semiconductor there are two kinds of charge carriers or two components of current, one due to electrons and the other one due to holes. So there are two kinds of charge carriers basically, electrons and holes. Now in an n-type semiconductor, because electrons are in abundance, the majority carriers are electrons, or the major component of the current is due to electrons. And this major component of current is independent of temperature, because these majority carriers are given by the donor impurity. They are not generated as a result of a fluctuation in temperature. These electrons or these majority carriers are not a result of the ionization process. These majority carriers or electrons have been donated by the donor impurity. Therefore, the major part of the current, which is due to these majority carriers, is now independent of temperature. However, because of course the process of ionization and recombination are nevertheless taking place, the minority carriers inside an n-type semiconductor are holes. And these minority carriers or holes are obviously still dependent on temperature, because these are still being generated as a process of ionization, which in turn is dependent on temperature. Now similarly, in a p-type semiconductor, the majority carriers are holes and they are independent of temperature, because these majority carriers or holes, they have been donated or contributed by the acceptor impurity. The minority carriers over here are electrons. They are of course dependent on temperature, because they are a result of the process of ionization which in turn is dependent on temperature. Pretty much like N-type semiconductors, over here the density of holes in a P-type semiconductor is the same as the density of holes donated by the acceptor impurity. And density of electrons in a P-type semiconductor is equal to Ni square divided by the density of holes donated by the acceptor impurity. Now, as semiconductors have two kinds of charge carriers, electrons and holes, similarly current in semiconductors is also flows due to two mechanisms. There is drift and there is diffusion. Let's first look at the drift current. Drift current flows due to an application of an external voltage source. So when you apply an external voltage source, it creates a certain electric field. As a result of this electric field, electrons and holes flow. The flow of electrons and holes is physically in opposite directions, but because these are two different types of charge carriers, their charges, one is negatively charged, the other is positively charged, their physical flow, which is in opposite direction, gets added, and the resultant current is in the same direction. So the figure over here, it shows the current that flows due to drift, which is the flow of current due to an application of an external driving force. Now the second current, which is due to diffusion, is a result from the natural tendency of charge carriers to move from a region of high concentration to a region of low concentration. We know from our previous study, we know from our education school that if we spray a certain air freshener, or if we spray a perfume in one corner of the room, due to a process of diffusion, that good scent or that good smell spreads throughout the room, because the molecules, they are in high concentration at one place, so they have the natural tendency to move towards the areas of lower concentration. So similarly, over here in this figure, as you see, that if holes are injected in this side of the bar, and one side a lot of holes are injected, they tend to move through the rest of the bar due to the process of diffusion. So this graph over here, the x-axis is the distance from the beginning of the bar to where the holes were injected to as we move across the bar, and we see that where the holes were injected, their concentration was maximum, and then as we move along, the concentration of holes reduce. So the diffusion current in semiconductors arises due to the different concentrations of charge carriers at various parts inside the semiconductor material. The charge carriers tend to flow from the regions of their higher concentration to regions of their lower concentration. So summarizing, there are two mechanisms by which current inside semiconductors flow, and those are drift and diffusion.